All right, good morning. We've got a midterm coming up. It's time to do a little bit of reviewing. So let's talk a little bit about how this will work. I've got a sets of practice problems posted in Canvas, and we'll be going through those. I feel like it's handy to have a review session and look through some sample problems, and then I want to talk more broadly about what other sorts of problems could be coming up on the midterm. The midterm doesn't consist of these particular problems. Understanding these problems and having a good handle on them is going to help, as well as kind of looking at all your homework. So take a look at all of the homework problems and the examples that we've looked at in lecture. So these just happen to be a few additional problems that gives us one more chance to go back and kind of talk about what we've been doing over the past 4 weeks or so. So let's go ahead and get started. And so on this, I've got 4 questions on one page. I've got 4 questions on one page and an additional 4 questions. I realize one of these overlap, but let's go ahead and take a look at these. These are problems that have shown up on previous year's exams. And so, you know, one thing you can be thinking is, well, at least it's kind of like practicing the format of one of the exams. And so on problem 1, what we've got here is a beam of light passing through a glass sphere. So the sphere has a radius of 10 centimeters, and the path of the incident light is 5 centimeters away from an axis that passes through the center. So what that's doing is it's giving us an idea, it's really giving us an idea of at what angle is the light running into the sphere. So it's not hitting it directly. If it hit it directly, there'd be no refraction. It could go right through and come out the other side, again with no refraction. But it's hitting it off axis, and the off axis distance is 5 centimeters. And so away from an axis that passes through the sphere. The index of refraction for the red light is 1.550. For the violet light, 1.570. Now, since we have different indices of refraction, we're guessing what's going to happen here is we're going to create a rainbow effect, right? The different wavelengths of light will spread out. And so what the problem's asking about is follow these paths of the red and the violet light through the glass, back out through to the air, and then from that we should be able to calculate at what angle the light is spread out, right? We're going to create this rainbow effect. Maybe this is some really pretty designer thing that goes, you can set it on a desk or something. I don't know, it's a doorknob. And it's going to create these rainbow patterns. It's going to look really pretty. So we want to find out what the dispersion angle is of the light that comes out from the sphere. Now, as we talked about in lecture, these refraction kind of problems involve geometry. Going back and remembering there's 180 degrees in the 3 angles of a triangle and things like that. And so, in addition to the geometry, of course, is the refraction formulas. And so I'm going to write down the refraction formulas. At the first surface, I'm going to call that theta 1, theta 2, theta 3, theta 4, kind of like what we did in lab when we were looking at the angles there. And N1 and N4 are just air. So I'm going to replace that with just a 1. I'm just going to drop those factors. And then N2 and N3 are the index of refraction of the glass sphere. And so for those, I'll just put in N. So I'm trying to simplify the notation here. And then the angle, the incident angle, if I start drawing normals to that surface, right? There's going to be a refraction that takes place there. So I'm going to draw a normal to the surface at that location. Now when I draw the normal to the surface of a sphere, and I continue that path on, it's going to go through the center of the sphere, and that's going to become a radius. And so I now have a radius to the sphere that has the same angle, theta 1, as the incident angle of the light. And that theta 1 I can calculate because I know the hypotenuse and I know the vertical distance on that side. And it turns out that the incident angle is 30 degrees. Now, that incident angle applies to the whole spectrum of light, right? The red light's coming in at 30, the orange is coming in at 30, the yellow, the green, the blue, the indigo, the violet, they're all coming in at 30 degrees at that initial angle. Now, since I know the initial angle and I know the index of refraction, I can calculate theta 2. And theta 2 worked out to be 18.82 for the red light. Now, the violet light has a different index of refraction, and that worked out to be 18.57. Did I ever write my... Oh, I did. There they are right there. So the violet light has a little larger index, and theta 2 turns out to be a little bit larger. Now, when it comes time to calculate theta 3 and theta 4, what I find is that there's so much symmetry because I'm working with this sphere that whatever angle the light comes in at, the path of the light across the sphere, it can't help but form an isosceles triangle. And so theta 3 is going to match theta 2. Now I know it's isosceles because two sides of the triangle are the radius of the sphere. So it's a bit of a geometry trick, I guess, to recognize that theta 2 and theta 3 are the same angle. Now, if theta 3 is the same as theta 2, I know from working with refraction and the refraction formula, well, theta 4 is going to be equal to theta 1. You know, the refraction that happens on the first surface will happen in opposite order at that second surface. So there you go. We really only have a couple of angles that we have to deal with because theta 3 equals theta 2 and theta 4 equals theta 1. Ooh, I should have completed the table though. I take a risk of losing points here. I was not very clear about my theta 3s and my theta 4s, even though I do have that written up in that portion. So, what do we got here so far? We drew the path. Okay, so drawing the path counts for something. Typically it does on most of these problems. So practice drawing your paths. You know, when you draw paths and you practice drawing good diagrams, it'll help you see what's going on in any case. And so I want there to be an incentive here for you guys to practice doing these drawings. Don't just look at a bunch of formulas, draw pictures. The picture sometimes, it'll just make sense when you see what's happening in terms of the picture. So we got the picture drawn, we got all of the angles figured out. Now we're going to find out the total dispersion angle. How hard could that be? Now, at first you might think there's no dispersion because theta 4 matches theta 4. But we realize now that the theta, the theta 4s that we calculate, it's true, it's going to be 30 degrees and 30 degrees. So both of the theta 4s are 30 degrees. Does that mean that the light's coming out parallel? And it doesn't. And the reason why is because the two paths that we draw are not coming out at the same location. The purple, the violet light, bends a little bit more, and that means when it comes out, it's at a different location. So how are we going to determine what the dispersion angle would be? Now there's an alternate way to do this, and that would be to calculate deflection. What we can do is say when the light came in, it's deflected once, and then it's deflected again. And if I compare the light coming in to the sphere with the light leaving the sphere, the angle between those is the sum of the two deflections. Now, the first deflection was theta 1 minus theta 2. If I look at that first angle and I ask myself, compared with the light coming in, how much of a deflection do I have? That path is bent downwards by theta 1 minus theta 2. Now, at the other deflection, or at the other refraction, I'm also going to have an additional deflection of theta 4 minus theta 3. Well, theta 4 minus theta 3 is the same thing as theta 1 minus theta 2. So what we can do is take the difference between these two and double it. Now, the difference here is 12 or 11.18. I double that, it's 22.36. So the red light going through bends by 11.18, and then it bends by another 11.18. So the total deflection is 22.6. The violet bends more. The violet bends 22.86, and then an additional 22.86. So when they come out, the two paths will be separated by half a degree. This will create a dispersion angle, which means what's the angle between the red and the violet light? Typically the rest of the spectrum, it's a continuous pattern where the index of refraction gradually varies from that for red all the way through towards the value for violet. Right? So that's the plan. Okay? Questions on that? Let me know. Let's move on and take a look at this next problem. Now, the first problem was kind of a chapter 32 problem. It dealt specifically with refraction. There's also reflection problems that could come up, certainly on the midterm. So again, we have homework problems on these. We have examples from lectures that are all excellent problems to go back and review, go back over those, as well as the ones that we have here. Now, chapter 33, there's a lot of stuff in chapter 33, so 33 could even spill over to more than one problem. We'll see what happens here. But in problem 2 on here, which is coming from chapter 33, it says that we have a lens. Oh, I forgot about mirrors. So remember mirrors also in chapter 32. Here's a lens, focal length of 20 centimeters. Object is placed 60 centimeters. It's converging. You know, it sounds like kind of the simplest possible lens we could end up with. Let's see if that's really going to be the case. And so what we've got here is, here's the location of the lens. Now they first of all want us to draw a ray diagram showing where the image is located. And so I got my ruler, I've got my, well, I guess that's about it. I got a straight edge, and I can draw these diagrams. And so I've got this drawn, I draw perpendicular to that, I place an object, I draw in the focal points on either side, and then first path is parallel, and then goes through the converging lens and comes back through the focal point. My favorite path, as always, the one that goes right through the middle. And then wherever that intersects, that's going to be the location of the image. Now, we said drawing that third line is a good way to double check and see if everything's making sense. So I'm going to use that other path through the other focal point and then come out parallel, and it worked. All three, hey, that was hand drawn. All three paths crossed that image right at that point, and it worked. Okay, and so let's see. Oh, I see. This is a later part of the problem. So the screen comes in later. So in part B, we're solving for the image distance. That the math tells us 30 centimeters, and yeah, we could have guessed that from our diagram, right? That's at 30 centimeters. And then the magnification is negative. There's an inversion. and it's going to be negative 0.500. All right, so the math matches the diagram. Everything's looking good. Now, this is a real, I think it asked that, right? Oh, here we go. It's a real image. It's a real object. And the image is inverted. And we can get that from the calculations or the diagram or both. Now, in Part D says that what we want to do is set a screen 10 centimeters farther beyond. Now, a screen is placed there in order to produce a sharp object. We're going to use a diverging lens with a focal length of negative 20. Where should we place the diverging lens? Ooh, what does this remind you of? And I hope it reminds you of lab number 2 when we had lenses, right? We were, in that lab, we were determining the focal length of the lens, and we used a combination converging, diverging. So let's see what happens here. Now this could get a little tricky. It looks like it's getting a little detailed here. So there's a screen, and the screen is 10 centimeters beyond that, what we've called an image. Now that image is going to become the object for the diverging lens. So the idea here would be to place a diverging lens before we get to the image, and then the diverging, because after the image is not going to produce an image on the screen. So I've got to put it in front of where that image is. And so I've drawn a diagram here. So I am saying that, make sure we got everything figured out here. So here is where the diverging lens is going to go, and here is where its object will be, and here is the screen. And so what we are solving here is x is 10, yeah, there we go, that's what I was looking for, is x is 10 centimeters. So there is my x, and that's 10 centimeters, and there is the DO, and there is the DI. And so what I've got is I've got a DI, the full distance here, which is equal to negative DO plus x. Now the reason that's negative is because my DO is going to be negative. So I want to use DO the distance, DO the magnitude, and so I put a minus sign in there with x. And then what I did is I wrote down the focal equation here. 1 over f equals 1 over d plus 1 over 1 over di, sorry. And di is this. And so I wrote that as x minus do. And then I cross-multiplied everything, which is a nice algebraic exercise, and got rid of the common denominators. And my numerators now say do times x minus do equals f times x minus do plus f times do. Now, that, when I write that out, it turns into a quadratic. And I'm solving for whatever I can solve for. And so what I'm going to solve for here is do. I know what x is. I know what f is. So I solve this as a quadratic. And I'm careful with quadratics. I know that, I don't know how you guys are, but I have a reasonably high failure rate with quadratics. I usually end up doing them a couple times. The DO answer that I got was 5 plus or minus 15. Now, when I looked at that answer, I know that the DO's got to be negative. I've already decided that the DO for this to work is going to have to be negative. I'm choosing the negative solution here. The positive solution would do what? I guess that would take me back. Yeah, I'm not sure how that would fit inside there. Okay, there's probably some physical reason why that solution showed up, but I'm going with the one that is negative 10. So if that's negative 10 and x is 10, well then di is 20, and the diverging lens then needs to be 10 centimeters from the object, 20 centimeters from the screen. It all fits, it all works together. The diverging lens needs to be 20 centimeters from the screen. Okay, so that last part, A, B, C, D. Now, the way that these get graded typically, if I have an A, B, C, D portion on an, which I always do on a question, usually I divide the points up pretty evenly. So, and then often in a question like this, the questions may get progressively more difficult. At the end of the question, a part D or E might be more challenging. But just remind yourself, even though it's more challenging, it's going to take more time, it's not necessarily worth more points. So don't panic if you don't get that part of the problem thinking maybe that's where all the points are. That's typically not the case. And then also make sure that as you're going through these problems, if you get to something like this and it seems like it's going to take way too much time, go ahead and move on. Now I know that's always a little bit dangerous on midterms because once you've started thinking about the problem, if you then stop and go do something else and come back, sometimes that works, sometimes it starts to make sense, sometimes you've forgotten and you have to kind of start over, but if need be, move on to a different problem. Don't end up spending the whole exam on a problem. Make sure, this is one piece of advice I always give, make sure that you get at least a reasonable look at each part of each problem. If there's parts of problems that you haven't even read by the time the exam's over, I'm not sure if that's the most efficient way. Just getting a few things down on each problem will be worth a fair amount of partial credit. Okay, and by a few things down, I mean something that actually shows you understand what the starting setup consists of. All right, problem 3, let's move on here. So problem 3 is looking at 3-slit interference. Now this is kind of interesting because we spent so much of chapter 34, I hope, thoroughly understanding how to set up a problem and combine interference effects to make a prediction about intensity patterns on a screen. So this is an example of bringing in one more slit. We now have 3 slits. The coherent light source just means that when the light comes in, this is in the lectures, but that everything when it starts out is in phase. So everything is in phase to start with, and then the light comes in, hits the 3, and then we start looking at different locations on the screen, deciding, what the interference effects will be. So first of all, it says draw a diagram of the phasor diagram. Draw the phasor diagram and show the sources and relative phases. And so what I've got is A, and A, and there are my relative phases, delta and delta, and the A total will be, the total of those distances with the phase angles included. Now in B it says calculate the net amplitude and the intensity as a function of phase difference. Now I can take, this turns out to be a simple enough diagram. The 2-slit interference also is a simple enough diagram that we can just do a little geometry on this and flip this thing over and show where all these phase angles are. And then I can break up this A total. There's a central portion of A total which has a length of A, and then on either side there's an A cosine delta. So I wrote that down. I may have, I did switch it over. It said to write it in terms of phase. Uh-oh, I'm in trouble. Losing points, I can see those points drop off. Boy, it does say phase difference. Find the phase differences and M values that produce intensity. So I kind of didn't stick with the phase as long as I needed to. I switched over to M too quickly. So anyway, wherever there's a delta, that's been replaced by M times 2 pi, but I could have just left the delta in there. So this seems fine. I got the A total. Now I have an intensity, and the rules for going from A total to intensity is that I take the A total and I square it. I modulus square it, but the modulus is irrelevant here because we're not yet working with complex amplitudes. And so I just have to square this expression. Now when I square it, and the square is right there, I can just write that expression, 1 plus 2 cosine m2 pi squared, and then I can put an I naught out front. And what that's saying is the intensity is proportional to the amplitude. So the intensity will be proportional to whatever the intensity of light is along the screen. And so I can just put an I naught out here and not worry about other factors that come in. Now, I didn't have to put the 3 down here, but I did. I'm kind of following the pattern that the textbook has used. What the textbook tends to do is they define I naught. I should have had a graph here too. Where it's down here, I guess. We tend to put I naught as the peak intensity. And so what I did was I looked at what's the largest value I could have in the numerator, and then I divided by that number so that the intensity never gets larger than I naught. That way, when I get down to my final graph here, the I naught value is the one that appears at these integers. All right, in part D, it looks like the maxima are going to occur at integer values of m. What I want to do is have this cosine become 1, and the cosine is going to be 1 whenever m is 0 or 1 or 2 or 3. That will give me 1 plus 2 over 3 is 1. That will give me the intensity is the peak intensity. So at 0, or at 1, at 2, on the screen, all of the 3 phasors will line up together. Now, what about the zeros? Where am I going to get these 3 sources to cancel out? Now, remember, with 2 sources, what we had was, one source would exactly cancel the other, and so that would be m is equal to 1/2. But now I have 3 sources, and if each source is shifted 1/3 cycle compared with the rest, those will cancel out. Now it turns out also, if the phasors shift by 2/3 of a cycle, that also produces a closed set of amplitudes. So this is kind of interesting. If we have 2 sources, there's 1 0 in the middle. But if I have 3 sources, there's 2 zeros between each set of peaks. And so here are the 2 zeros that we've got at the 4/3 and the 5/3 down in part D, I guess it is. So in part D, they give us a wavelength of 500. They give us a, did they give that to us? Let me see. They did. D is equal to 10,000 nanometers. And so I have 500 nanometers and 10,000 nanometers. I can use my D sine theta equals m lambda. And I can start putting numbers in for m equals 1, m equals 2. Now it asks for the angular locations of any zeros within that range. So, yeah. So the ones in between 1 and 2 would be m values of 4/3 and 5/3. And so I've got all the angles written down for that. All right. So it's a good extension of what we did in chapter 34. It's a good chance to go back and practice extending that. What would 4 sources look like? That's got to be going through, you've got to be thinking that now. All right, problem 4 says this. It says we have a diffraction grating, and the diffraction grating is going to be used to take visible light between 400 and 700 nanometers and spread it out over 20 degrees. So how should I build it? What should be the specifications? how many rulings or how many lines, how many slits, those are all kind of used interchangeably, per millimeter in order to have a diffraction grating that will create this 20-degree separation. So I started this problem by writing some stuff down. So here's my diffraction grating. I said this, I don't know why I put the red light at 90 degrees. I said, okay, there's an angle theta 1 over to blue, there's an angle theta 1 over to red. D sine theta 1 equals lambda 1, D sine theta 2 equals lambda 2, where wavelengths 1 and 2 are for the blue and the red. And I want the difference between the two thetas to be 20 degrees. Now, I played around with it algebraically a bit. This was a problem that I ran across, where was that? In one of the, maybe in the textbook, or a different textbook. And I wasn't making much progress algebraically. It was taking quite a bit of time, so I resorted to guessing. Now, not just random wild guessing, but what I realized was I had some pretty simple formulas here that I could work from. So I took these two formulas and said, look, sine theta 1 over sine theta 2, that's got to be the ratio of the wavelengths, and that's always going to be 4/7. So what I did was I started guessing. I said, what if sine 1 was 20 degrees? If sine 1 is 20 degrees, then sine 2 is 36.77, and I got that from this equation right here. And then I said, okay, for those two numbers, what's my delta? And it was 16.77, and I thought, you know, that's actually pretty close. What if I just do a few more lines of guessing? So my next guess was 30 degrees, why not, right? And for this, theta 2 was 61 degrees, and now my delta jumped all the way to 31. I go, no, it was too big of a jump. 10 degrees increase was too big. I went back and tried 22. And when I tried 22, I ended up with theta 2 at 41, which was 19 degrees. That's actually pretty close. I tried 23, which gave me 43.1, which is a difference of 20 degrees. And then I started going down into the tens, and I got down to 22.9. So it took me 6 guesses, but you know, it was sensible sort of guessing, until I got something that came back with 20-degree separation. And so I thought, fine, great, I've answered the question. I don't have to do it in closed algebraic form. I can do it by a series of approximations and demonstrate that's the answer. So I wrote down theta 1 is 22.9, theta 2 is 42.9. 42.9. When I put that back into these formulas, both of them gave me a D value of 1028. Perfect. So I've found a set of numbers that meets all of the three requirements that I was given. It satisfies the angle, distance, wavelength requirement for blue. It does the same for red. And then it also satisfies the difference between angle requirement. So fine, we found it. And then I took the D and I switched that over into number of etchings or rulings, or what else do we call them? Slits, lines. 972 of those per millimeter. That's going to give me the angles that I want. Okay. Now once I got this solved, I thought, you know, I really should go back and see if I can do the algebra. So I did. And it filled that page. So what I ended up doing here, just to give you a brief rundown, is I put delta is equal to theta 2 minus theta 1. I know what delta has to be. It has to be 20. So I can work in terms of delta. And then I used some trig identities. I went back to some sum of angles, actually some difference of angles here. And then I knew that sine 1 and sine theta 1, sine theta 2 had to be equal to lambda 1 and lambda 2. because m's equal to 1. This is for a first order spectrum, is what the problem asked for. And so I used the trig identities. I substituted here, I took out the cosines and replaced them with sines, because I know what the sines are, and then I switched those over into wavelengths. And it turned into kind of a mess, and then a few things canceled out. There was a lot of drama here, but I got to this formula. So I was able to put it in, it's not always a guarantee, but I was able to get this in closed algebraic form. Lambda 1 squared plus lambda 2 squared minus 2 times lambda 1 lambda 2 cosine. It looks kind of like the law of cosines or something. Square rooted over the sine of delta, and look what I got. I got 1028.6. So over here I had gotten 1028. So pretty good, it worked. Anyway, that's the first page. We should probably take a break right there. So let's take a break for a bit and we'll come back and look at that second page of problems.